We are in Chapter 6, the normal distribution. This is Section 6-3. This is video recording number 2. Okay, where we left off was we were right here talking about the properties of the distribution of the sample means. And this is edition number 10. This is the official textbook edition. And if you're using that edition, this is page 344 is where we are. Okay, so here's the properties of the distribution of the sample mean. Okay, now let's read this carefully here because it gets confusing. When all possible samples of a specific size are selected with replacement. Now, as I mentioned, it doesn't make any sense sometimes because we are going to replace people after we sample them, but that's the theory here. The distribution of the sample means for a variable has two important properties. Now listen, this is in general, this is the generic distribution of sample means. It doesn't say anything about being a normal distribution. This is the properties of the distribution of sample means. We haven't gotten to the concept of normality yet, or that it's a normal distribution. Okay, the mean of the sample means will be the same as the population means. What in the world does that mean? The sample means are the x-bars, right? The x-bars can be considered as a random variable. Since the x-bars are a random variable, why wouldn't you expect them to have a mean? It makes sense, right? It's the mean of the sample means. I wish I could change the language here. Unfortunately, we're just kind of stuck with it. It's the mean of the x-bars. The average of the x-bars is what we're talking about here. The second important point is, since the x-bars are considered to be a random variable, they can also have a standard deviation. So what is it? What can we say about it? The standard deviation of the x-bars will be smaller than the standard deviation of the population, and it will be equal to, we can actually write down a formula for it, it will be equal to the population standard deviation divided by the square root of the sample size. Now, let's not worry about the formula yet. Let's just think about it. Is it logical? Is it rational? Is it fit your intuition that the standard deviation of the sample means will be smaller than the standard deviation of the population? Well, it fits my intuition, because what we're saying is that the x-bars are not as widely dispersed. They're not spread out. The x-bars are not spread out as all the data points are for the population. And that fits my intuition, right? I mean, because it's just kind of makes sense that when you take a sample, you're going to have less dispersion. It's not going to be as spread out as the original data points are. And you'll see as we go along, I think that intuition will come to you when you see some examples. So here's an example to illustrate it. Okay, now of all the places to have typos, I wish he would have picked a different place to have typos, because it's confusing enough. This whole section is confusing enough. The following example, and there's going to be a typo here in just one second. The following example illustrates the properties. Okay, you got an 8-point quiz to a small class. There's only 4 students, and there's 8 points. The results of the quiz were 2, 6, 4, and 8. So, Billy got a 2, Johnny got a 6, Susie got a 4, and so forth, okay? For the sake of this discussion, let's assume that the 4 students constitute the population, just to make things simpler for us. So therefore, the mean of the population is, well, we know how to do this. We know how to calculate the mean. It's you add up the scores and divide by however many are in the population. This is a mu, so that's the mean of the population. As opposed to a sample mean. It's not an x-bar, it's a mu, right? Okay, so it's 2 plus 6 plus 4 plus 8 divided by 4, boom, is equal to 5. The standard deviation of the population, again, using sigma here, the standard deviation is, okay, the top part is fine. Remember the formula? I wish this guy would write down the formulas. The formula is the various data points, the various, the x1 is x1 take away mu plus x2 take away mu and so forth. Okay, so obviously this is in your book, but just for your convenience to kind of keep the flow going here, this is from the book. This is the one of the at the end of chapter 3. This has the various formulas. Okay, now the important formulas you should know by now are at the end of every single one of the chapters for that chapter. Okay, so back in chapter 3, where we're talking about actual data points, actual data, as opposed to probabilities, we learned how to do these calculations. So it was for the mu, it was this: you sum up all of the data points, the values of the data points, and then divide by the total number of elements or guys that are in the population. I hate to use the word guys. It doesn't sound very scientific, but that's the definition for mu. The definition for the variance, sigma squared, is you take all of the data points, all of the x guys, the x sub 1, x sub 2, x sub 3, and so forth, and what do? You add up these deltas, these differences. It's x1 subtract the mu. We got the mu over here, and the mu is just a number, so x1 take away mu, the quantity squared, x2 take away mu, quantity squared, add them up. x3 take away mu, quantity squared, add it up. So you keep on adding these guys, and then you divide by the total number that are in the population. So that's for the sigma squared. The that's for the variance. The standard deviation, of course, is you just take the square root. I hope you remember all that. Okay. All right. So let's go back to the book. Okay. So as you can see, that's exactly what he did here. That's just the formula from chapter 3. Add up these data points: 2 plus 6 plus 4 plus 8, etc. The standard deviation, unfortunately, here's the typo. He has the square root up here. Okay, that's fine. Okay, but down below it should be the square root of 4. It's the square root of n, right? Here it is. It's the square root of the entire thing. It's not just the square root of the top, it's the square root of the entire thing. So it should be the square root of the denominator as well. And unfortunately, there's that typo. So it should be the square root of 4 down here. Or another way of writing it is just take the square root of the entire fraction. That's what I'm sure what he meant to do. Okay, so a little tiny bit awkward here, to say the least, that he would have a typo right there. But if you were looking at that and going crazy, hopefully I helped you understand it. Okay, so here's the graph of the original distribution. Okay, it's a histogram. It's a frequency distribution. Now remember that what I've always said is that a frequency distribution tells you how many did you really get of the random variable, whereas a probability distribution, the y-axis is not the frequency, it's not how many. The y-axis in a probability distribution is how many do you expect to get, or what are you expecting? What's the probability of getting it? So in essence, the way I always think about it, just as a stupid way of helping me remember it, for frequency distribution and probability distribution. For frequency distribution, I think to myself, frequency distribution is what have I got? And then probability distribution, what do I expect? Okay, that's the difference. So now the frequency distribution here, one of the kids got a 2, one of the kids got a 4, one of the kids got a 6, one of the kids got an 8. So that's the distribution. Okay, so this is what we call a uniform distribution. There's no change. I mean, there's one of each of these random variables. Okay, so now if you took all samples of size 2, and again, it's a little bit fictitious here. We're doing it with replacement. Obviously, you would not really do that. This is just illustrating the point. So if all samples of size 2 are taken with replacement, and the means of each sample are found, this is what you get. Okay, so it's a sample of size 2. So I got 2 and 2, 2 and 4, 2 and 6, 2 and 8. You see what's going on here? You're picking these guys, picking that random variable. Okay. All right. So yeah, you go ahead and do this. Go ahead and I'll let you read through this yourself. You do this, and what do you get? You get, for the first guy here, 2 and 2. What's the mean? Is 2, right? 2 plus 2 is 4. Divided by 2 is 2. The next guy, 2 plus 4 is 6. Divided by 2, that's my n. Divided by 2 is 3. 2 plus 6 is 8. Divided by 2, that gives me 4, and so forth. Okay? So that's easy enough. So now, again, I keep stressing this. I want you to make sure you understand that the X bar can be a random variable. So the X bar has its own frequency distribution. Boom, here it is. How many times is X bar equal to 3, let's say? Well, let's see. Here's 1, and that's it. There it is. There's 2 of them. How about 5? How many times is X bar equal to 5? Well, here's 1, 2, 3, 4. Oh, nuts. Try that again. 1, 2, 3, 4. I got 4. What does he get? He's got 4 too. Okay, so you have a distribution, a frequency distribution of the X bars. He keeps calling it sample means, but it's the X bars, right? Okay, so now this guy right here, this frequency distribution, the frequency distribution of the X bars has its own distribution. There it is. So this is a different histogram. This is the distribution of the sample means. Before, we had a distribution of the scores, the test scores. That was the raw data. Now we have a distribution of the sample means. Okay? Well, it's by golly, this is a distribution. You can't. I'm sorry, what I really meant to say is this is a distribution of a random variable. The random variable is sample mean. We don't discriminate just because it's an unusual, for us, it's an unusual random variable. It still has all the properties. Well, so the mean of the sample means, and we're going to do it like this. It's going to be mu with a little subscript of X bar. We take those guys, we add them up, divide by the total number of guys, okay? I'm going to let you verify that all that makes sense there, okay? And what do we come up with? We come up with 5. So the average, the mu of the X bars is 5. That's the same as the population mean, and verify that, okay? So mu sub X bar is equal to mu. The standard deviation, well, unfortunately, here's another typo. Remember, the sigma, the standard deviation is the square root of the variance. So it should be the square root of the top and of the bottom. So it should be square root of 16 down here. I think when he calculates it out, he does it correctly. He just has a little typo there. Okay. Now, okay, so as he says right here, it's the population standard deviation divided by the square root of 2, which I wish he'd write down the formulas. It makes it so much better when you write down the formulas every single time, and that comes from up here. The standard deviation of the X bars is smaller, and it is equal to the population standard deviation divided by the square root of the sample size. Okay, in summary, if all possible samples of size n are taken with replacement from the same population, the mean of the sample means, the mean of the X bars, we're going to call it this, equals the population mean, mu, and the standard deviation of the X bars, we're going to denote that by sigma sub X bar, equals sigma divided by the square root of n. The standard deviation of the sample means is called the standard error of the mean. So here's what we typically call it, okay? So it's just a new terminology. So the third property of the sampling distribution we're now going to introduce, and this is the real punchline of all this, and it talks about the shape of the distribution, and we're going to find out, hey, what the heck? It's the normal distribution. Okay, so that's the end of this tape.